Hiya, 13. Let us have a look at your first quantum nuclear physics lesson. I should be allowed back in school tomorrow, so lessons from now on should be back in person. Touch wood, unless I get ill with something else. What a ridiculous month it has been. So before we start lesson one, which is called Photons and the photoelectric effect, I just want to refer to the word quantum and make sure that you're understanding what I mean by that word. So quantum mechanics is the general area of physics that we're looking at for this topic. And it's a fundamental theory in physics that describes the behavior of nature at the scale of atoms and subatomic particles. So everything that we talk about in this topic only works, and the equations only work, and the laws only apply on the microscopic scale. So you can't apply these theories and equations that we're about to learn on day-to-day life. They just don't fit. So it's the foundation of all quantum physics, and it explains how things behave at a very small scale, but it doesn't scale up. So the word quantum itself is a minimum amount of a physical entity involved in an interaction. So it's the smallest possible value that anything can take within quantum physics. So kind of imagine breaking things down into smaller and smaller parts. The smallest it can possibly be is a quantum of that value. Quantization can be an S or a Z, depends on American versus English spelling, is the systematic transition from a classical physics understanding to a newer understanding. So it's basically us taking what we thought we knew on a day-to-day classical mechanical level, so everything that we've learned so far basically in physics, and changing it and adapting it so that it still makes sense when we make observations at a microscopic level. And then quantized is applying quantum theory to anything, basically. So to restrict the number of possible values of a quantity or states of a system, so that certain variables now can only take very discrete values and magnitudes. So quantizing something basically means you no longer have a spectrum of values that are allowed. There are only very discrete, specific numbers that are possible to give to a value. So that, kind of introduces the concept of quantum physics. Is basically saying, right, all the laws that we have up until this point no longer make sense when we are looking at things at the level of atomic and subatomic particles, and we have to rewrite the rules of physics. So lesson one, sorry, is called Photons and the Photoelectric Effect. And then your syllabus points are there. You have to know what they are, and then you have to be able to discuss an experiment that we have that basically supports quantum physics and the concept of a photon, more on which later. And then you have to basically be able to look at this experiment in graph form and also mathematically. So the first thing to maybe write down is this phrase, wave-particle duality. You may have heard of it before. You probably have, knowing you lot. You've probably watched many videos on it. So wave-particle duality is a concept within quantum mechanics that says that light and matter, so everything that you've learned about light and matter so far is that light is a wave and matter is particles, is thrown out of the window. And we now say, okay, hang on a minute, both light and matter can behave in a particle way and in a wave way. So light can now not just be seen as a wave, but it can also be seen as a particle. And matter can not only be seen as a wave, but also, not only as a particle, but also as a wave. So this, I'm going to keep throwing this phrase at you, wave-particle duality. It's pretty revolutionary, really, because everything that we understand about the world before this point is that we have waves and particles and they're completely separate things. And then quantum mechanics has come along and said, no, hang on a minute, actually, everything can be both. So light can be both a wave, but it can also act as a particle. Particles are particles, but they can also act as waves. And there's two pieces of evidence that you need to learn about in this topic to basically say, well, we've got this evidence that suggests that wave-particle duality is a thing. The photoelectric effect, which is today's lesson, which is evidence for light having wave-particle duality. So that's the focus of today. And then later in the topic, we will look at electron diffraction, which is evidence for particles having wave-particle duality. And so everything that we do, and we'll kind of go into the nitty-gritty details, what I need you to keep reminding yourself of is the whole point that we're learning about this stuff today is to provide evidence for this idea that light is no longer just a wave. It can be both. So, a photon is the name given to a particle of light. So if we're thinking about light and we think of it as a wave, and then we take a certain amount of that wave, a piece of energy of light is called a photon. So the energy of a photon is quantized. So what that means is it has a very specific value. We will learn more about this later. A photon is something that you can consider to be a wave packet, so a packet of waves. So take an amount of a wave, and it's now a particle amount. It still moves at the speed of light, but it acts like a particle. So we have two equations that will really kind of underpin this entire topic. So E equals mc squared allows us to quantize the energy of a particle with mass m, and E equals hf allows us to quantize, so find the discrete amount of energy that a wave photon has, which is the particle equivalent of a wave. I will explain what those things mean later. But what you need to know now is that if I use the word photon, I'm basically describing a particle of light, okay, an amount of light, a discrete amount of light. So today's lesson is about the photoelectric effect. We're going to look at that. We're going to see that it basically provides evidence to support the theory that waves can be particles. Lesson objectives are here. You can pause if you really want to read them, but I'll be doing all of these things today. So I usually start this lesson with an analogy, but then I've come to realise in the last couple of years that if you didn't grow up in England, you might not actually know what this is. So let me first explain. You can see in the picture there's something called a coconut shy, and if you look really closely you can see white posts, and at the top of each of them is a coconut. And then you can see a child about to throw a ball and try and hit one of the coconuts off the stand. And basically the game is that if you knock it off, you get to keep the coconut. Fun game. So if you understand the concept of a coconut shy, you'll now be able to think about the analogy. So question one is, what would happen if you tried to knock a coconut off its stand just using a ping pong ball? And then my second question is, what would happen if you used 100 of those ping pong balls? And then my third question is that if you used a cannonball, what would happen? So you should hopefully understand that if I try and knock a coconut off a stand with a ping pong ball, it's never going to get knocked off. Wouldn't matter if I used 100 either. If I threw 100 of them at the coconut, they're still too light and the coconut's not going to get knocked off. It's only with the cannonball that the coconut will get knocked off. Sorry. You might think I've gone mad, but this will hopefully help you to remember the photoelectric effect later. You will see why. Hold that thought and bear with me. But you should hopefully understand that it needs the cannonball to knock the coconut off. Okay. Task 1 in your printed pack says, what is the photoelectric effect? Add some notes and a diagram. I think I printed the diagram for you. So the first thing is you need to fundamentally understand what I mean by the photoelectric effect. We take a piece of metal, we shine light on the metal, and it turns out that we see that sometimes electrons start spontaneously leaving the metal. So electrons that were part of the metal atoms suddenly just leave because light has been shone on the metal surface. Okay, it's just something we've observed. So it is a low energy light matter interaction. Okay, so we've got light interacting with a piece of matter, a metal, and shining photons onto the metal plate causes emission of electrons. That is the photoelectric effect. Photo meaning light, okay, electric meaning electron. The effect of shining photons, aka light, onto a metal surface means that the metal emits electrons and they leave the surface of the metal, they're no longer bound to the metal. Okay. Sometimes you might see the electrons that have been emitted in this effect referred to as photoelectrons. They're still electrons, there's nothing special about them, it's just that the word photo shows that those electrons have been freed from their metal because of photons. Okay, that is what the effect is. It's as simple as that. And this provides evidence that light acts as particles. You will see why later. Pause this video and add that to your task 1 for me. What is it? It's as simple as photons shining on metal surface, electrons are emitted, and we call those electrons photoelectrons. Okay, that's step 1. Pause me here, and then we'll carry on. So, in task 2, you are going to see 4 observations that are made when we do this experiment. It's simultaneously the most boring experiment, but also the most mind-blowing experiment for me, because it is literally just shine a light on a piece of metal, watch what happens. But what we can surmise from it is wild. Okay, so your job is for each of the 4 observations, you need to draw a diagram that represents each one. And then what I'll ask you to do is I'll give you an observation and then you will draw a diagram and then you'll carry on. So I will give you an observation. I will read it out to you. This is observation number 1. And then I'll show you the diagram that I did. And I'm basically asking you to try and actually critically think about what the yellow box says and put it into a picture form, because if you can do that, I know you've understood what the yellow box says. So try not to skip ahead and just copy blindly, but try and actually interpret it yourself and put it into a picture yourself. It's where the learning happens. So we've just said that the photoelectric effect is where electrons are emitted from a metal surface when light is shone on it. This does not happen every single time that light is emitted from the surface of a metal, right? It happens sometimes, and that is the photoelectric effect. But there are cases where you will not get electron emission, and you need to know these observations. So, number 1, the photoelectric effect does not occur if the incident radiation frequency is below the threshold frequency for that metal. Okay, so we have this concept of a threshold frequency for a particular metal. Gold, silver, magnesium, aluminium, all the metals have their own individual threshold frequencies. And basically what that means is the light that's being shone on the metal has to at least meet that threshold frequency for the metal to emit electrons. I can send as much light as I want, crazy intensities, a load of energy, doesn't make a difference. I will not get electron emission unless the frequency of that light is meeting the minimum threshold frequency. Okay, that's observation number 1. Draw a picture to represent that for me. Pause me while you do it. And then once you hit play, I will scroll and show you what I drew to represent that. Okay, so this also links back to the EM spectrum, topic 4 waves. So you can see I've got 3 different wavelengths and therefore 3 different frequencies of light. Okay, so you can see that the low frequency light, which is red, does not cause electron emission for this particular metal. Threshold frequency has not been met. As soon as the threshold frequency is met, I get electron emission. So green and violet lights all have frequencies that have met the threshold frequency for the metal, and electron emission does occur. You will also notice, hopefully, and more on this later, that the electrons are emitted with more energy with the violet light, which should hopefully make sense to you because violet light is more energetic than green. Okay, so that was observation number 1. Observation number 2 is that the number of electrons emitted per second, and we can count this, is proportional to the intensity of the incident radiation. Okay, I should specify that intensity is power per unit area. Power is energy over time. And so basically what we're saying is the intensity is a measure of how much energy per second is reaching a surface area of metal. And the number of electrons emitted per second, sorry, my voice is struggling with this today. The number of electrons emitted per second is directly proportional to the intensity, but only if the threshold frequency is met. Okay, below the threshold frequency, doesn't matter what the intensity is, nothing happens. But so long as the threshold frequency is met, we move on to our next condition, which is that if the intensity increases, the number of electrons emitted per second increases. Draw me a diagram to represent that. Pause me. And then when you've done that, carry on. So this is what I drew. Okay. Each photon we know has an amount of energy. So the more photons we have, the more energy we have total hitting a surface area, which means the intensity goes up. So you can see I've got 2 photons emitting 2 electrons, 3 photons emitting 3 electrons as my diagram for observation number 2. Observation number 3, and this is really important, is that photoelectric effect emission occurs without delay. It's instantaneous. So the instant the radiation hits the surface is the instant the electrons are emitted. Again, so long as the threshold frequency has been met. Okay, so we are not saying that light is being shone and after a certain amount of time electrons are emitted. We are saying that the instant there's interaction between the light, the photons, and the metal surface, we get electron emission. Okay, it's instantaneous. That's a hard one to draw a diagram for. I just drew a clock to represent that at exactly the same time as photons hitting, you get electrons being emitted as well. Okay. Observation number 4 is that the maximum kinetic energy of the electrons that have been emitted is proportional to the incident radiation frequency, but it is independent of the intensity. So what I'm saying here is that when electrons are emitted, because the threshold frequency of the light has been met, the electrons are emitted with a kinetic energy that is proportional to the frequency of the light. But the kinetic energy is completely independent of the intensity. So I can bombard with 1,000,000 photons or 1 photon, and the kinetic energy of the electron emitted will be the same in both cases. Okay, it's only proportional to the frequency of an individual photon. So the diagram I drew here shows the low frequency red light, no electrons are emitted because the threshold frequency wasn't met. The slightly higher frequency green light, the threshold frequency has been met, and the energy of the photon, the green light photon, is quite low, and so the kinetic energy of that electron is low, its velocity of leaving will be low. And then the higher frequency and therefore higher energy violet light will mean that the kinetic energy of the electron is higher, and therefore the maximum velocity that the electron leaves with will be higher. So there's a proportionality between the frequency and basically the speed of the electron leaving. But it doesn't matter if I send in 1,000,000 violet photons or 1 violet photon, each electron kinetic energy value is determined purely by the frequency of one of those photons. Okay, it won't become higher because there was more light shined on the surface in terms of photon number. So I'm going to go back to my analogy and now make you think about how that maybe represents the photoelectric effect. Hopefully you should notice that the coconut represents the electron, and if it gets knocked off and falls to the floor, it has left the surface, but if it stays, it hasn't. The ping pong ball and the cannonball both represent photons of light, but of different frequencies. So the ping pong ball has very low frequency, and the cannonball has very high frequency. Okay, so with the ping pong ball's low frequency, it doesn't matter how many of them I throw at once, nothing is going to knock the coconut off. Okay, so the frequency of the light is too low to do anything. And even if I have a million of them, a million of those photons, I'm not going to be able to knock the coconut off. The cannonball has high frequency, high energy with it. And so even one of those will be able to knock a coconut off. I don't need a million of them. And so that was the analogy there. And it's just a way for you to try and remember it, because there's a lot going on here. Okay. So basically, this entire lesson is saying that, okay, hang on a minute, light actually is able to act like a particle. And up until year 13, you've only thought of light as a wave. And we need to basically explain why the 4 yellow observations that I've just made cannot be explained by light acting as a wave. Because up until this point, you could just say, well, hang on a minute, everything that you've just said could still maybe be explained by light being a wave. But actually it can't, and we need to really go into detail here. So my question is, what can the wave theory of light, so light acting like a wave, not explain what we've just seen? Okay, so we've just seen 4 observations. Why do wave theory not explain that? So the 2 things that cannot be explained by wave theory is, firstly, the existence of a threshold frequency in the first place, and secondly, the fact that it occurs instantaneously without delay. Now, the wave theory of light says that over time, light is transferring energy to the electrons. And it would suggest that over time, every single electron in the metal should be gaining some energy from the waves, regardless of how many waves arrive per second. Okay, and it basically says, well, hang on, if the light is a wave, eventually the electron will build up enough energy from those waves that it can escape the surface. So why is it that doesn't happen sometimes? Okay, so there are some implications, things that we have kind of figured out based on what we've seen when we've done the photoelectric effect. Observation number 1 was that the photoelectric effect just doesn't even occur, doesn't happen. Doesn't matter how long I shine low frequency light, it just does not cause electrons to be emitted. That implies that there is no building up of wave energy over time to give electrons enough energy to leave the plate. Okay, if light was only a wave, eventually the low frequency light would have been able to transfer enough energy, because the whole point of a wave is that energy is transferred over time. Okay, but we see that just doesn't happen all of the time. If the energy of the wave is too low, if the photon frequency is too low, it doesn't matter how long we shine it for, nothing happens. And so it implies that suddenly the wave isn't acting as a wave anymore. Okay, it's not taking time to build up energy. There must be an instant transfer. The second observation, which is the number of electrons emitted per second being proportional to the intensity, supports this idea of a photon, because it basically supports an interaction of one photon with one electron. Because as the intensity of light increases, what we're saying is the number of photons in that surface area increases, meaning that each photon can interact with an electron. More photons means more electrons involved in the interaction. In number 3, we said that the photoelectric emission occurs without delay. And so this implies that we have a discrete, quantized amount of energy being transferred from the light to the electron instantaneously. There's no build-up over time. The photon interacts with the electron, transfers that energy immediately, the electron can leave. And then number 4, the maximum kinetic energy of the electrons being proportional to the instant radiation implies that one photon interacts with one electron, and that photon having different amounts of energy means that the electron can leave with different amounts of energy, different amounts of kinetic energy. Okay, so it implies that there's a one-to-one interaction between one photon, a particle of wave, and one electron. I've summarised this in a table. I'm going to pause and not read it out to you because my voice is getting croaky and sore, but you can also just read. Okay, so on the left we have the observations, things we see happen. Then in the middle you've got why the wave model is no longer good enough to explain light, and why we've moved to a photon model where we now think of light acting in particle form, and how that can be explained, or how that can explain the observations. So pause me. It might be helpful to write it down. I can also print it for you when I'm back, whichever you'd rather, but really take your time to read this carefully. Okay, and then move on when you're ready. Okay, so hopefully by now I have convinced you that waves can act like particles. And we have said that the name of the particle of light is a photon. We know that the energy of a photon is proportional to its radiation frequency, but it doesn't have any mass. We need to be able to quantize the amount of energy a photon of light has. And Einstein took the work of a guy called Max Planck, and he came up with another equation because it's like he hadn't done enough already. Okay, he took the Planck constant, which is the constant that Mr. Planck came up with. It's a new one. And he said that the energy of a photon is proportional to frequency, and the constant of proportionality is the Planck constant, which is in your data booklet. You'll probably know it anyway by the end of this topic without having to look. So E equals HF. The energy of one photon can be given by the frequency of the light multiplied by the Planck constant, which is given on the bottom of the screen. Okay, so please write that down. It's task 5 in your booklet. We also know from our study of waves that the frequency of light is given by the speed of light in a vacuum divided by its wavelength. Those things still stand. Photons still travel at the speed of light and still have wavelengths. So an energy amount of one photon of light, one particle of light, can also be quantized and found by hc over lambda. We're just substituting in. Okay, so the energy of a photon is inversely proportional to its wavelength. So we've got two equations, E equals HF and E equals hc over lambda. Okay, and those will both be given in joules. Okay, so they'll be measured in joules. Pause, write it down. The thing is, we also know that we've got a handy unit of energy, which is called an electron volt. Okay, so we know that we can express energy in joules, but we also know that we can express it in electron volts. Now we know from topic 5, electricity, that work done is given by charge multiplied by potential value. Okay, so voltage times charge is the energy transferred. So the energy gained by one electron when it has been accelerated through 1 volt is known as 1 electron volt. Okay, so 1 electron volt by definition is when 1 electron is accelerated through a potential difference of 1 volt. Q is 1 electron, V is 1 volt. Okay, when we take the charge of an electron, so 1.6 times 10 to the minus 19, and we multiply it by 1 volt that it is accelerated through, that work done is called 1 electron volt. So we have an equivalency. Okay, so 1.6 times 10 to the minus 19 joules can also be phrased as 1 electron volt. This is a much tidier number and it's helpful in a lot of equations. So please write down that equivalency so that we are able to use it so that we can talk about energy in electron volts and energy in terms of joules. Okay. I said at the start we had to think about the photoelectric effect graphically. Okay, so this is an IB multiple choice question and it links to what we've just talked about. So it says, ultraviolet light is shone on a zinc surface and photoelectrons are emitted. The sketch graph shows how the stopping potential, more on that phrase later, Vs varies with frequency f. So we've got a voltage value on my y-axis and a frequency on my x-axis. Planck's constant may be determined from the charge of an electron E multiplied by what? And it gives you some options. Okay, Looks tricky, but you can do this. If you want to completely ignore what's on the right-hand side, just, I don't know, pull the video over so you can't see all of it and try it yourself if you want to. Otherwise, have a look at this little derivation with me. So above the orange line are things we know. Below is how we use them to get the answer. So we know that the energy of a photon is equal to hf. H is the Planck's constant, which is what the question is asking us to find from the graph. We also know that work done is QV, charge multiplied by voltage. I can rearrange this for voltage, because that's all on y-axis. And I can say that therefore it's equal to the work done per unit charge. Okay, V is E over Q. We know that the Planck constant can be found from my first equation, equals HF. I've rearranged it to say H is equal to E over F. And I know that Q in my equation here is charge is going to also be equal to E, because that's just the charge in this particular question. So the gradient of my graph is y over x. In this case is voltage over frequency, V over F. And I have substituted in my teal-green equation, V is E over Q, into this equation. So my gradient can be expressed as E over QF. I also know that the E over F part of that, the pink bit, is the Planck constant. So what I've said is that the gradient is V over F, which must be equivalent to E over QF, and that the E over F is the Planck constant, and I've separated out my E over QF to be E over F times 1 over Q. Now what I have is the Planck constant, E over F, is H, and I know then that the gradient of my graph must be equal to H times 1 over Q. I know that Q is the charge of the electron, and so I could also replace that with H times 1 over E. And so if I take the gradient of the graph and I multiply by Q, it means I'm multiplying both sides of this equation by Q. And so the gradient times Q must equal H. And therefore, H, the Planck constant, comes from the gradient of the graph multiplied by charge. And so therefore, I know that because in the question it says Planck's constant may be determined by the charge multiplied by, I know that the answer is then the gradient of the graph. And so the answer to this question is C. Okay, take some time with that one. Okay, pause at that point. We move on to something called the work function of a metal. Okay, we're almost at the end of me talking at you, I promise. So we can define the work function a metal has. It's given by the symbol phi, which looks like an O with a line through it, vertical line through it. Okay, so work function phi of a metal is, by definition, the minimum energy of that is required. Sorry, I'm flagging over here. I've been talking for a while. Let me say that again. Phi, the work function of the metal, is the minimum energy required by an electron to escape its surface. Okay, so energy is basically needed to be able to release the surface electrons because they are attracted by the electrostatic forces in the metal ions. So we know that in metals, electrons are free to move, which leaves positive metal ions behind. So those electrons that we are causing to escape the surface are still attracted to the positive metal ions, and so energy has to be transferred in order to release them. Okay, and the minimum energy needed is known as the work function, just purely because of the electrostatic forces. Okay, so you can see that when we have a low energy, low frequency red photon shining, it cannot transfer enough energy to overcome that potential well. So this idea of a potential well is like trying to allow it to escape the surface, and the deeper the well, the more energy required. So we know that each metal will have a particular potential well, a particular amount of energy that is going to be needed to escape. And so the red photon here is too low energy, too low frequency, and it's not going to transfer enough to allow it to escape. It will give it some excitation energy, but it will not be enough to escape. And then there will be a particular photon energy that matches the work function that gives it just enough energy to escape. And then any higher energy will allow the work function to be met, but there will also be additional energy that's been transferred. And so not only will the electron leave the metal surface, it will leave with more kinetic energy. Now, I've tried to preempt questions that you have. And so I've added a bit of extra information. You might be thinking, well, why is it only an electron at the surface? Does it not apply to all? So I did a bit of research. So the work function of a metal does apply to all of its electrons. It isn't just the surface electrons. The work function is a property of the metal that quantifies the energy required to remove the electron and move it outside of the metal. And it's linked to the binding energy, which we'll talk about later, of the electrons in the metal that are valence electrons that are free to move. But it's important to note, especially when dealing with the photoelectric effect, that the work function is only discussed in terms of surface electrons because those are the ones that will have been involved in the electron emission, because they're the ones that will interact with the photons. So for IB level, we're only talking about the surface electrons, because those are the ones that are most likely to have interacted with the photons. Okay, so that's why we say it's to escape its surface. So we just saw that there's a minimum amount of energy that the electron needs to leave, but that any extra energy given will mean that the electron can leave with more kinetic energy. So we can summarize that as an equation. The incident energy transferred comes from the photon, E equals HF. So that's the left-hand side of my equation. HF is transferred to the work function, the minimum energy to allow it to escape, plus any extra energy that has given will be given to the kinetic energy of the electron, half mv squared. Okay, so that's where this equation comes from. Incident energy is given to the work function to escape, plus any extra is given to the kinetic energy. Okay, I can rearrange that. I can say that half mv squared is the kinetic energy maximum of the electrons emitted. So rearranging, I can say that the kinetic energy maximum is equal to HF minus phi. Okay, so emission can take place from a surface so long as the kinetic energy maximum is greater than 0, and therefore HF has to be greater than phi. And that explains why the threshold frequency has to be met. We have to be able to provide enough energy. Okay, so the threshold frequency minimum for a metal, F0, that's a new term, comes from setting minimum energy being 0, meaning HF minus phi equals 0, meaning HF at a minimum has to equal phi. I'm saying then that H must be equal to phi over F, or F must be equal to phi over H. Okay, it comes from setting this equation minimum to be 0. Okay, I think these might be the last two. Yes, they are. Oh, good, and then I can stop talking. Okay, so graphically, I can now plot a graph of the frequency of incident radiation on my x-axis and the maximum kinetic energy of my photoelectrons. And we said that the kinetic energy was proportional to the incident frequency, so we can see a straight line graph. Okay, but we know that there's some minimum threshold frequency that has to be met. Okay, so we've just said HF, the photon frequency multiplied by the Planck constant, equals the energy transferred, because that's the energy of the photon being transferred to the electron. We know that it is equal to the sum of the work function and the kinetic energy maximum. Okay, you can see kinetic energy is my y value on this graph. My x value is frequency. Okay, which means that the gradient of my graph must equal the Planck constant, and my y-intercept must be equal to minus my work function, okay? So if I plot a graph of maximum kinetic energy against frequency, I know that the y-intercept will equal the work function and the gradient will equal the Planck constant. See if you can work that out yourself. I've just quickly skipped over, but you can pause and go backwards, and I'll go back in a minute. But see if you can remind yourself from my equation here, rearrange it so it's in the form of the graph y against x, and then work out what the values of the x-intercept, the y-intercept, and the gradient must be equal to. And if you can do that, then you've got your head around the equation well. Okay, and then once you've done that, you can go back on the video and check your answers. And then you are going to go to the practice questions that I'm going to post as a form on Management. And you can check that you've understood everything that this video has gone through. I know it has been a lot. We're not going to go past this point, even though the slides do. That's been a lot of me talking, a lot of you digesting information, but hopefully it has made sense. But make notes of any questions you want to ask me when I'm back. All right, there you go.